In this problem, you know L is a linear transformation. You know that L of 1, 0 is the vector 3, 5, and L of 0, 1 is the vector 2, negative 1. You want to find L of 2, 3. This is not a proof, but I thought it would be nice to go through the strategy with you. First thing I do is I consider this vector 2, 3. I also consider what I know. I know L of, well, actually, this is the unit basis vector, E sub 0, and this is E sub 1. I also know that any vector can be written as a linear combination of some scalars with unit basis vectors. So I can write this as 2 times E sub 0 plus 3 times E sub 1. Why will that help? Because L is a linear transformation, which means L of 2, 3 is equal to L of 2 times E sub 0 plus 3 times E sub 1. But since L is a linear transformation, this is 2 times L of E sub 0 plus 3 times L of E sub 1, which means it's 2 times L of E sub 0 is the vector 3, 5, plus 3 times L of E sub 1, which was 2, negative 1, by looking at this linear combination. 2 times the vector 3, 5 is the vector 6, 10, and I want to add to it 3 times the vector 2, negative 1, which will have components 6, negative 3. When I add these two vectors, I get the vector 12, 7, if I did my arithmetic correctly. So the idea is, if I want to evaluate this linear transformation at a particular vector, and I know some values, if I can write this vector as a linear combination of the vectors I know how to evaluate this linear transformation at, then I can use the fact that it's a linear transformation to determine or evaluate the linear transformation at any point that can be written as a linear combination of the vectors that I know.